let us take a look at the effects of radiation. Now, the thing is, the side effects of radiation are not very nice. Radiation can cause a number of things. Now, remember, when I'm talking about radiation, I am talking about alpha, beta, and gamma. Now, basically, exposure to too much radiation could cause mutation in your DNA. Now, you might not notice that directly, but any children you have in the future, it may become apparent then. Mutation could also cause a tumor, which is a big growth. You could have a brain tumor or tumors elsewhere. And some tumors can kill other cells, and this could also lead to cancer. Now, obviously, cancer itself is not a very nice thing. Now, here's the thing. Whilst radiation can cause cancer, radiation can also kill cancer, it has to be pointed out. But the overarching principle of this slide is that radiation is not good for us in too much doses. Precautions. Now, there are a number of precautions that you can take when you are using or handling radioactive substances. Some of them, I would say, are more pertinent than others. Definitely store your radioactive materials in a locked cupboard. Not only a locked cupboard, but if it was in a lead container, that would be even better. Display the radioactive warning sign like you would see in hospitals or you would see around nuclear power plants. But for us, for the normal man or woman, you would be most likely to see it in a hospital near the X-ray department. Don't spend too much time using the radioactive substance. Now, to me, that's probably bottom or towards the bottom of the pecking order. It seems a little too obvious. Recording each time they're used could also be useful, but for me, the most useful ones are storing it in a lead container, the radioactive source, handling it with tongs or forceps, not your own hands, wearing protective clothing such as a lead apron, or wearing a radioactive badge. And like I said, I also mentioned displaying the radioactive warning sign. Not spending too much time and recording each time they are used would be bottom of my pecking order. Uses of radioactivity. Here, we're going to look at their applications. Whilst many people think that radioactivity is a bad thing, radioactivity or radiation can be very, very useful. So, let's look at the thickness monitoring of paper. Now, how does this work? You only need to know it in its most simplest terms. You're not expected to know how computers work and the feedback loop works. In principle, what you have to understand is when you are monitoring the thickness of paper, you would use a beta source and not an alpha or gamma source. Why wouldn't you use alpha? Well, alpha doesn't pass through paper. In fact, alpha doesn't even pass through 6 centimeters of air. Gamma, on the other hand, would go through the paper very easily. And not only that, the way this experiment here is designed, it will probably go through the ceiling. So that's not very useful. Whilst beta is stopped by 3 millimeters of aluminium, there will be an impact with paper. So what happens is, when the paper is too thick, less beta particles are detected by the detector. If the paper is too thin, then more beta particles will pass through. Now, if too many beta particles pass through, the computer adjusts the machine to make the paper thicker, and if not enough beta particles pass through, then basically it will adjust itself to make the paper thinner. Incidentally, earlier on I said the gamma would go right up the way and through the ceiling. The source actually is at the top here. My mistake, the gamma would go through the floor underneath. So this is why you would pick beta. You wouldn't pick alpha because it wouldn't pass through paper. You wouldn't pick gamma because it would pretty much pass through anything. So once again, if the paper gets thicker, then less radiation is picked up by the Geiger-Müller tube, and then the machine will adjust itself to make the paper thinner. If the paper becomes too thin, too many beta particles are detected, and therefore the machine adjusts itself to make the paper thicker. It's like your air conditioning. Your air conditioning, when you set it to a certain temperature, the air conditioning turns itself on and off without you thinking about it. It doesn't work with radiation. The principle that I'm trying to highlight here is the fact that it is automatic. Carbon dating. Now, I was always amazed with carbon dating as a child. I always used to wonder how they knew how old a mummy that, you know, came from one of the pyramids or the tombs in Egypt was. So how do they use this? Well, basically, we all have radioactive carbon-14 inside our body. When we pass away, that radioactive carbon-14 begins to decay. It takes 5,700 years to decay. Now, let's just give an example. Let's pretend that we know that a living creature has 100 carbon-14 atoms. And let's say, making a few assumptions, we could compare that with a mummy from Egypt. And let's say the mummy has 25 carbon-14 atoms. Well, I hope you understand, to go from 100 to 25, we have halved twice. From 100 to 50, we halved once. From 50 to 25, we halved 2 times. If we know the half-life is 5,700 years, well, basically, we know the age of the mummy by doing 5,700 times 2. Here we are again with measuring the thickness of paper, just so you can see this in more detail. Here, the machine is controlling the thickness of paper, and the beta source is passing through the paper, and it's being picked up by the Geiger-Müller tube. As mentioned before, if too much radiation passes through, the paper is too thin, so the machine makes the paper thicker. And if not enough radiation passes through, basically the paper is too thick and the machine makes it thinner. Radioactive tracers. Now, radioactive tracers are often a gamma source. Why gamma? 2 reasons. In general, gamma is the least ionizing of the 3 radiations. And secondly, basically, it pretty much penetrates anything. You would have to have very thick lead and concrete in order to pretty much stop gamma. Why is it useful in industry? Well, here in the top picture, we have someone that's looking for, let's say, an oil leak. So let's say we've got these oil pipes underground and they realize there's a leak somewhere because not enough oil is getting to the other side. The industrialists would insert some gamma radiation as an isotope, a liquid, along the pipes. And then one of the employees would go along the surface with a Geiger-Müller tube. It looks like a metal detector here. They would walk along the surface, and if they're getting a good count rate, if they're picking up radiation, they know that the oil is flowing along this stretch of, let's say, road, for example. If all of a sudden the gentleman in the top picture here walks past the leak, then the Geiger-Müller tube will pick up a lower radiation count. If he picks up a lower radiation count, he would walk backwards until he picked up the high radiation count round about here. This will tell him this is exactly where the leak is. So they would then come along, dig the turf up, whether it's sand or soil, and repair the cracked or burst pipe. Radioactive tracers can also be used in medicine. God forbid, let's say I had some sort of blood clot in my arm, a radioactive tracer would be injected into my bloodstream. Again, it would be a gamma source. Why? Because it can be picked up from outside the body. Not only that, it's the least ionizing, so the least harmful to me. The other thing that it should have is a very short half-life. Why? Because by the time I leave the hospital, I definitely don't want any radiation going off in my body. So, we inject this radioactive isotope, we take the Geiger-Müller tube or detector around my body, and if there's a good count rate, we know the blood flow is okay. But let's say we get to my arm and all of a sudden the count rate goes lower. So we've got as I get lower and lower. What that then suggests is there's some issue in my hand, that there could be a blood clot there. So good count rate would mean radiation is flowing no problem, or the blood is flowing no problem. Poor count rate would mean there is a problem. The blood's not flowing as easily. There could be a blood clot. The doctor would then know exactly where to look. Killing cells, such as killing cancer. Now in radiotherapy, gamma rays are fired at cancer cells to kill them. Okay, so basically a gamma knife, as it's called, can be used to be directed at the cancerous cells to kill cancer. Yes, radiation can cause cancer, but radiation can also kill cancer. So we can use it in a machine called a gamma knife to fire gamma rays into our body to kill the cancerous cells. For example, here's a cartoon of Einstein here, and he is going to have a gamma knife fired at a cancerous tumor, for example. Not a nice thing to think about, but radiation can be used for good. Why use gamma? Gamma is highly penetrating. It will get through the skin, it will get through the bone, and it will target the cancer. Now, this is not something that I would recommend, but radiation can be used to kill bacteria in food. My preference would be to use the radiation to kill bacteria in hospital equipment. Radiation can be used to sterilize hospital equipment.